Yeah, so today I'm going to talk about what James has kind of hinted at, open source driven innovation in the data center and, the software driven hardware concept and what it means and a bunch of projects that are associated with it, the kind of things that my company Antmicro does to kind of drive more innovation in the data center space. A little bit about us. We've been around for 12 years now, and what we do is providing engineering service to build open source platforms, tools, and do R&D for customers that build high-tech products. We work with all sorts of industrial IoT topics and edge to cloud AI systems in various domains of the industry. Most notably, perhaps, we're kind of members of various initiatives that can coordinate the next generation of open source platforms, the Linux Foundation, the Zephyr project, as well as, of course, Open Power Foundation, Chips Alliance, and RISC-V. Our expertise covers the whole technology stack. So we kind of work from hardware development, even dabbling in ASIC development, FPGA stuff, through software, artificial intelligence, and up to cloud, up to different kinds of tooling for those areas. And specifically in the data center space, we work with hyperscalers and big corporations to re-energize their data center space and development to add this energy from the open source software ecosystem into hardware. We're looking at new design methodologies. We're working with different workflows that enable hardware people to kind of tap into this capabilities that open source offers them that have been traditionally associated with software. And by doing this, we try to enable more vertical integration, full control of your technology stack. It has been a very recent trend, very popular trend these days. Everyone is trying to build hardware. We're trying to also kind of work with our customers to show them how to build hardware in even better, even more collaborative ways, and especially to give them the ability to rapidly iterate with their solutions. Okay, one of the projects I wanted to mention here today is an open source FPGA-based BMC. And this is being developed as part of the LibreBMC project under Open Power, which James has mentioned. And the motivation for it has been that we saw, low-cost FPGAs of today being able to actually replace traditional ASIC-based BMC without a big problem. We can run pretty powerful soft CPUs inside an FPGA. In this way, we can actually give the developers more control over hardware because, FPGAs, as you know, are configurable pieces of hardware. You can change whatever's in them. So this gives you an ability to rapidly iterate and develop and improve security. And we took the DC-SCM standard here as a baseline because the DC-SCM standard being a module that you use for the BMC is very convenient. It's, the modularity aspect is already built into this. So building an actual module that has an FPGA on it that also allows you to kind of reconfigure said FPGA however you wish is kind of a very powerful concept here. And also, since we think that vendor neutrality and portability is kind of an important aspect of every development, we decided that we're going to also kind of support various FPGAs in this context to kind of show the ability to put the same thing in different FPGAs and make them work as if they were pretty much equivalent. So I'll show you a little bit of this in a second. This fully open source BMC platform originally was developed by Antmicro in collaboration with Google. And this is a piece of hardware that's compatible with Open Compute Project's DC-SCM 1.0 specification. So what it is, it's an FPGA-based board, and it has both an open source design in terms of the hardware, but all the firmware, gateware, software that we're developing here, this is all meant to be completely open. It's also a great use case for the typical toolchain that we're also developing, which is an open source FPGA toolchain, meaning that the tools to develop and program those FPGAs should also be open, so that like the entire tooling flow is open source. This again, kind of this aspect I was talking about. We want to, for people working with hardware, to have this agility and this rapid iteration capability and the insight into their tools, just like traditional software developers have. The DC-SCM module that we developed has the ability to plug in external root of trust and trusted platform modules into it. So it's kind of modularity and modularity. And it can run both Linux and Zephyr RTOS. There are 2 hardware variants, and of course, there will probably be more. The first one is ARTIX DC-SCM, or what we call the ARTIX DC-SCM, because it has an ARTIX 7 FPGA on it. It uses the DC-SCM horizontal form factor and has quite a bunch of I/O interfaces. I mean, this is pretty much defined by the standard, so we can kind of take a look at that list here. And of course, all the design files for this board are fully available, and there's a blog note describing this development, so I encourage you to read more about it later. As for the current status of this hardware, it's undergoing bring up. It has been successfully kind of put into a AC92 server. That there is a specially designed interposer that was designed to kind of host this module. Currently, it's very hard to get like an actual DC-SCM server. And the board will be on display on the OCP Summit, and there's going to be a talk by Todd Rosedal from IBM with the title kind of listed on this slide. So we encourage you to participate. The OCP Summit is next month. But there's also an ECP-based version. So this is a Lattice ECP5 FPGA-based equivalent module. So again, a very similar set of IOs. All the design files are available on our open source portal and GitHub. Basically, this shows that you can kind of migrate between different FPGAs and get the same functionality. And the components we're using, LiteX and Linux and Zephyr RTOS and so on, all of these are kind of very well supported on both of these FPGAs. And of course, our company kind of works with a variety of server-oriented hardware, and we build different kinds of hardware and mechanical solutions for flexible and modular servers, such as scale nodes, kind of little server blade we built for the Raspberry Compute module form factor. We use that for different kinds of, custom CI board farms for hybrid testing solutions that we kind of have to work with due to our profile. We're developing a lot of FPGA-oriented tools or AC development tools or different kinds of OTA systems and so on and so on, or testing frameworks as such. So we kind of build this hardware for ourselves, but we also have customers who are interested and who are working with us on these pieces of hardware. And we're very happy to kind of take the platforms that we develop internally, publish them open source, and then work with our customers around those. The processing solutions that we're building currently, based on scale nodes, they're capable of doing ARM and RISC-V based processing. And of course, as James was mentioning, there's this new initiative of the PowerPi. So hopefully in the future, we also have a power variant. You'll actually be able to hear more about the LibreBMC later today, because there's a talk by Todd, pretty soon. Let me move on to Renode, which is the second part of my talk. So first up, a little bit about Renode itself. It's a kind of open source system development framework, or just simulator, some people say, but it's kind of much more than that. It allows you to do co-simulation, both in software between like regular simulation and HDL simulation and something very later, or software and FPGA. There's a very good kind of capability to accelerate your development, especially if you're developing kind of hardware-oriented systems. It's being used by a number of big players, and anyone that's doing IoT or ML development or building some kind of new silicon where they want to experiment and play around with things uses Renode. It supports quite a lot of different existing pieces of IP and sensors and some kind of networking blocks. We also, of course, have the ability to model things for people, and we have, in fact, worked with a bunch of teams building, SoCs before they were actually implemented in practice in silicon. And as I mentioned, it's being used for a number of use cases. Of course, one thing that this ties into the previous thing is that we can actually simulate something like LibreBMC because we can simulate I/O. We have different CPUs supported, including the micro-auth. We have the LightX peripherals that we'll be using in the LibreBMC project. There's some demos and blog notes about it on our blog. So generally speaking, Renode is great for this kind of security hardening and testing and rapid development that you need to build something like a LibreBMC. So the fact that we can kind of use Renode for this is very, very convenient. What's more, sorry? I think someone unmuted by accident. So Renode can also be used for different kinds of security-oriented use cases. And there is a lot of groups out there using Renode for security reasons. OpenTitan, Bitrusted, Dover Microsystems, that's actually a very interesting one. They have been developing, their own security IP in a completely hardware-software co-development methodology. So basically, they kind of look at whatever architecture is useful and feasible using RISC-V, and only then they actually implement it in hardware. So that's a bunch of kind of security-oriented use cases there. Also, when you're developing machine learning, there's quite a bunch of things you can do with Renode. Of course, again, there's a number of groups using Renode for this. Most, perhaps prominently, is the TensorFlow Light Micro team at Google. We now have support for stuff like custom function units, so kind of a machine learning playground from Google. We have the ability to simulate with Verilator, as I mentioned before. That's also very useful for kind of when you're developing a machine learning accelerator. You can kind of simulate that in Verilator and then simulate a bigger system in Renode. We have a bunch of projects running with this, and perhaps interestingly, we have a webinar today that's called Boost Edge AI Development with Renode Zephyr and Antmicro, hosted with Nordic Semiconductors. So just in case you can, feel free to join that. Okay, on to the third topic, which is the LPDDR or DDR testing platform. Basically, this is a project where we create an open source software and hardware system for memory security research. And this was built for and with Google, and helps us to kind of very flexibly research and improve security in different kinds of solutions, both on the edge and in the cloud. And so we have FPGA or a bunch of FPGA baseboards. We have software and FPGA IP in the form of Light DRAM, which is an open source DRAM controller, to try to mitigate a very common problem that's RowHammer. I'm going to talk about this next slide. So we originally started with LPDDR4, which was our primary target, but we're also kind of adding more and more as we go. And in fact, even DDR5 support is in progress. And potentially, we're going to put this out in ASIC form in 2022. There's a bunch of blog notes about this too. There's a link here in this slide. So what this framework does is it mitigates the RowHammer problem, or helps research and mitigate the RowHammer problem, which is a vulnerability of memory chips to physical phenomena that allow you to kind of manipulate memory that you shouldn't be able to. Our initial target was LPDDR4, so more on the edge, and we built some kind of cool modules and some research platforms, which already kind of resulted in a bunch of papers, and a new method, RowHammer method, was detected called the half double. That was already described in a paper by Google and already cited by a bunch of other papers. So it's kind of, this is really an active area of research. But now we're also bringing that to the data center. So we kind of talked to other groups at Google, and turns out that, well, the data center is also interested to research that kind of security, and we have a data center DRAM tester board. And this is also based on a Xilinx FPGA. It's open hardware, of course, and it supports RDDR4 RAM modules. This is work in progress, but it's kind of already pretty advanced, as you can see. So yeah, go ahead and check it out. I think it's pretty cool. And the LPDDR4 and 5 test framework and the RowHammer problem will be described in more detail by Tim Ansel later today as well. So summing up, we think that open source is really transforming the way data center hardware is built, just like it transformed cloud computing, right? Because the cloud was actually the original place where open source was a smash hit. So there's no surprise that data centers should work the same way. And we think that the open source approach and the tools and methodologies that we build can really help hardware people innovate faster. and get this benefit known from software. We think reuse is super important, and if you want to really kind of build stable solutions, just reuse things that are already there. And yeah, what can I say? Antmicro is there. We can help you move faster in this space. We can provide commercial support and engineering services. So feel free to reach out. And if you're interested to kind of learn a bit more about us and what we do, the kind of things we do, we actually have a technical showcase right on the main website. Down below, there's a plethora of different kinds of blog notes about different topics that you might be interested in. Okay, thank you very much. That's all from me.